Good morning, sir.
Good morning.
Good morning, sir.
Good morning. Anurag Tiwari या Tripathi?
Tiwari. Actually, both are almost same. Tiwari.
अच्छा अच्छा अच्छा. I'm all I know someone in NIT Uttarakhand.
Yeah.
His name is Tripathi.
Okay.
Mahesh.
Yes, sir.
Start
yes,
now.
sir. Tell me, sir.
अभी शुरू करते हैं या बाद में?
Anurag sir, how many participants are there now? Almost 20, 30?
Yeah, 25 around.
I think better to wait for 5 minutes. 11:05 we will start. Is it?
ठीक है, कोई बात नहीं.
Yes, sir. 5 minutes better to start. Right, sir? Thank you, sir. Okay, sir.
मैथ्स डिपार्टमेंट में कितना लोग हैं महेश?
Sir, we are total 5 faculty in our college, sir.
अच्छा. ओम कभी आए थे?
One of coordinator Shalini. Yes, sir.
हाँ. Okay. ओम आए थे?
Shalini came also with us. Where?
अजमेर.
Sir, you are talking about you.
नहीं, ओम सुतार.
Yes, sir. Sir, we did 2 times, sir. Twice.
अच्छा, good.
Still I am waiting as a arrival of family.
Oh, okay.
After marriage, he did visit. Yes, sir. Waiting.
Yeah.
He will join very soon.
You leave him alone. He is newly married.
Yes, sir. Yes, sir. Right, sir. That's why not forcing him to visit Ajmer right now. Whenever free, he will visit, sir. Definitely.
Yeah.
Sir, have you visited, sir, Ajmer?
हाँ, एक बार विजिट किया हूँ.
कब, sir? Which time, sir?
बहुत पहले, 15-20 साल पहले.
Okay. Now, when situation will become better, then sir, kindly visit once again whenever you have a free time.
Oh, जरूर.
Yes, sir. I will wait, sir, definitely for that. Yes, sir. And sir, as you are asking about our department, sir, we are total 5 faculty members in our department. And another faculty I want to introduce, Shalini Agarwal, madam. She is also coordinator of this program, sir.
अच्छा.
Good morning, sir.
Mute करो.
Good morning. Good morning.
Good morning, sir. Good morning.
Good morning.
Mute कर ले. Sir, which topic we want to cover today, sir? as you are asking about something finite difference method, I think, sir.
Yes, I'll do finite difference and then I'll take up what I want to say.
Okay, sir. Sure, sir. Sure.
Today, no problem, 90 minutes.
Okay, sir. Okay. Thank you, sir. Thank you.
Hello, Mahesh sir.
Yes, sir.
I think we can start. Okay.
Yes, sir. Tell me.
We can start now.
Yes, sir. You may introduce, sir, and then we will start. Definitely, sir. Please. It's
So, good morning to everyone. Welcome to fourth day session on this online short-term course on computational method in engineering science. So we have with us again with Professor P.G. Siddheshwar sir. He's the senior professor of mathematics, Christ College, Bangalore. So now again I would like to invite Professor P.G. sir to deliver their second lecture on this short-term course. Sir, can you can start now, sir.
Okay. Are you seeing the screen?
Yes, it's
Okay. Good morning, everyone. What I'll do first is I'll go through the finite difference method in some detail, I mean most of the aspects which you would normally require in an application. I'll just go through that, and subsequently I'll talk about two methods which are extremely useful. Computational fluid dynamics was thought of to be done by people who know sophisticated methods, but I'll show you two methods which we can easily use to do some complicated computational fluid dynamics problems. But first, the finite difference methods for differential equations, both ODEs as well as PDEs. I'll skip this part. I thought I'll first do it, but then I'll skip this. Electromagnetics. Yes. See, you should know that not all boundary value problems have a solution. If you take this boundary value problem, ordinary differential equation, y double dash plus y equal to 0, y dash of 0 equal to 0, y of pi by 2 equal to 1. So the general solution is y equal to c1 cos x plus c2 sin x. Then you use the boundary conditions now. So take the first one, that is y dash of 0 equal to 0. That will give you c2 equal to 0. So it means y of x is c1 cos x. But now you require to find out c1 such that y of pi by 2 equal to 1. That is simply impossible. Okay. So it means that this does not have a solution. Okay. But many problems do have a solution. And but we should be aware of problems which do not have a solution also. Okay. So in order to understand why we do numerics, you should know that there are many differential equations for which you cannot find that is an analytical solution. You would require the use of numerical method, that is approximate methods. Okay, so with some accuracy that is to be determined. So those things I shall just discuss. So in order to understand finite difference approximation of ordinary derivatives, you consider the Taylor series expansion of a function y of x plus delta y of x plus h. H is nothing but delta x. So you know this is the expansion. Now suppose I truncate after two terms. Okay, I forget about all these terms. So what happens? Y of x plus h is yx plus h into y dash x. So I'll rearrange for y dash of x. So I get y of x plus h minus y of x divided by h. Now I am writing truncation error is of the order of h. Why am I writing like this? See, if you see what I have truncated h squared by 2 y double dash plus h cube by 3 y triple dash 3 factorial y triple dash and so on. And when I write down the expression for y dash, what am I doing? I'm dividing by h. So that means even these terms are to be divided by h. So h by 2 factorial is what I am removing. H squared by 3 factorial y triple dash is what I am removing because I am dividing by h. So that means when I say order of h, it means term involving h, term involving h squared, h cube and so on. So now if h is very, very small, I have an approximation for y dash of x as y of x plus h minus yx divided by h. This is called as the forward difference approximation. Why is it called as the forward difference approximation? You want the derivative at x, so you are writing it in terms of the forward point x plus h and the current point x. Okay, so that is the reason why it is called as a forward difference approximation to the first derivative. So you know now why the truncation error is of the order of h. Likewise, we'll consider yet another function y of x minus h. So you know this Taylor series expansion. So now rearrange again for y dash of x, meaning I'll divide by h, and this will be h by 2 factorial y double dash h squared by 3 factorial y triple dash. So truncation error will again be of the order of h. So what will be y dash of x from here? That will be y of x minus y of x minus h by h. Okay, when h is very, very small, this is a good approximation. Now, why is it called backward? When you want to find out the derivative at x, I'm using the current point minus the backward point x minus h. Okay, so that is the reason why it is called as the backward difference approximation to the first derivative. So now I'll do one other thing. I'll take y of x plus h. From that, I'll subtract y of x minus h. So I'll get 2h into y dash x. Truncation error will be of the order of h squared. So y dash again has another approximation now. It is the forward point minus the backward point. Okay, divided by 2h. So we call that as the central difference approximation. Okay. Now, instead of subtracting, what I'll do is I'll add. I'll get an expression for y double dash. Okay. So y double dash will be y of x plus h minus 2yx plus y of x minus h by h squared. Since x will be in between x minus h and x plus h, it is the central difference approximation to the second derivative. Note that first derivative, the central difference approximation, the truncation error is of the order of h squared. Note that the central difference approximation to the second order derivative, the truncation error is also of the order of h squared. Now remember the following, h is quite small. So when I say h is quite small, it will be a quantity less than 1. So h squared will be much smaller. So when I say order of h squared, the truncation error is much less than the truncation error if it is order of h. So order of h squared is much smaller. So what happened? Am I sharing?
Yes, sir.
Yes.
Acha. Okay, so we looked into the forward difference approximation, the backward difference approximation, the central difference approximation for the first order derivative. So there are three choices for first order. Then second order, we have only one, which is the second central difference approximation to the second order derivative. Now, let us introduce some notation. When I say y of x, I don't consider all the points. I'm going to consider only some of the points, that is I times delta x. I equal to 0, I equal to 1, I equal to 2, etc. So I get h, 2h, 3h, and so on. So when I say h, x, it is actually xi, meaning ih. So the value of y at xi is yi. The value of y at x plus h, what is it? That is I plus 1h. So when I say y of ih, I am saying yi. When I say y of I plus 1h, what do I say? yi plus 1. When I say yi minus 1, what do I say? yi minus 1. Okay. So this shorthand notation. So when I take the central difference approximation, what is it? Y of x plus h. What do I have here? Y of x plus h minus y of x minus h. So what is y of x plus h? yi plus 1. Y of x minus h is yi minus 1. So yi dash is yi plus 1 minus yi minus 1 by 2h. Yi double dash is likewise yi plus 1 minus 2y plus yi minus 1 by h squared. So similarly, you can find out the finite difference approximation, central difference approximation to be precise, for the third order derivative, for the fourth order derivative, and so on. Okay, you can obtain that. So now let me solve one problem. This is a boundary value problem because the conditions are given at 2 points, 0 and 1. So this is a boundary value problem. So I want to solve this boundary value problem by finite difference approximation. So what is the interval of interest with respect to x? That is 0 to 1. So I have 0, I have 1. I have divided this interval 0, 1 into how many subintervals? I have divided this into 4 subintervals. So this length is x. This is x. This is x. And that is x. Okay, h. Sorry. That is delta x, delta x, delta x, and delta x. Delta x, I call it as h. So this delta x is 1 by 4. This is 1 by 4. This is 1 by 4. This is 1 by 4. When you add up all the 4, you will get 1. Okay. So now I'll finite difference approximate y double dash. What is it? yi plus 1 minus 2yi plus yi minus 1 by h squared. That is equal to, instead of x, what do I say? I say xi. Instead of y, I say yi. So now what is h? H is 1 by 4. So the 1 by 4 whole squared. So 16 moves to the numerator. So what happens? 16 yi plus 1. Then this becomes minus 32 yi. Then you have another yi on the right hand side. You push it to the left hand side. So that becomes minus 33 yi plus 16 yi minus 1. That is equal to xi. What are the unknowns? See, you see here y of 0 equal to 0. When I say y of 0 equal to 0, it is y not equal to 0. When I say y1, well, what is y of x? I'll go back again. I think it's better. When I say y of x, it is y of ih equal to yi. So when I want y0, I is 0. So I'll get y naught. Okay, so that is what I have obtained here. Y naught is 0. Y of 0 equal to 0. Now when x equal to 1, what is I here? 1 by 4. I mean, H is 1 by 4. So when I equal to 4, I get 1. Okay, so X4 is 1. So Y4 is 1. So I know X naught at X naught equal to 0, I have Y naught, which is 0. At X4 equal to 1, I have Y4 equal to 0. So I need to find out only Y1, Y2 and Y3. That is the reason why I am writing here I equal to 1 to 3. So I'll take I equal to 1 in this. I'll take I equal to 2 in this. I'll take I equal to 3 in this. And I'll note that Y naught equal to 0 and Y4 equal to 0. So Y naught equal to 0. And what is Y4? Y4 is also equal to 0. So I have written it here. So then I'll get this matrix in this form. Solving this, I get Y1, Y2 and Y3. You can solve it by any method. You can use Cramer's rule or Gauss elimination, Gauss-Jordan, okay, or Jacobi method, whatever. Okay, so this is what you have. So when X equal to 1 by 4, I obtained this value. Now the exact solution to the problem is Y equal to sin X by sin hyperbolic X by sin hyperbolic 1 minus 1. So you see that the error, if I subtract the exact value minus the numerical value at 1 by 4, I get 0.30. That means the numerical value and the exact value, they match up to 3 decimal digits. So this is the value at X equal to half. This is the value at X equal to 3 by 4. So you see there is quite a reasonably good matching between the numerical value and the exact value. Okay, so this is what you have. Now I'll consider another problem. Fourth order boundary value problem. So you have 4 boundary conditions which are given here. So I'll take a H equal to 1 by 3 here. I'll reduce one subinterval, mean the interval 0, 1. So H is 1 by 3. This is 1 by 3. This is 1 by 3. They'll add up to 1. So I'll finite difference approximate Y4 dash. I had done that earlier. So if I do that, I'll get this equation. What are the unknowns? I have I equal to 1 and I equal to 2 are the unknowns. Inside the region of interest. Y4 is a value which is outside the region of interest. Okay, so that means I am having outside elements now, Y minus 1 and Y4. Y0 and Y3 are 0. Okay, they are given from Y0 equal to 0, Y1 equal to 0, they give you Y0 equal to 0 and Y3 equal to 0. So if I use that, now I need Y minus 1 and Y4. So finite difference approximate Yi double dash. So take Y0 double dash. So it is this. Now you know the value of Y0, that is 0. So because Y0 double dash, that is 0, Y minus 1 will be the same as Y plus 1. So here what I do is I substitute Y of minus 1 to be plus 1. Okay, then I take the approximation Y3 double dash, which will give you Y4 minus 2Y3 plus Y2 divided by 1 by 9, because H is 1 by 3. So this becomes 1 by 9. Now you know that Y3 double dash is equal to 0. So what happens now? Y3 is Y4 is 0, Y3 is 0. So you will get Y4 to be minus Y2. Okay, so this is what you have. Here, I'm sorry, this should be Y minus 1 equal to minus Y1. Okay, so I'm sorry for this mistake. So if you use these two outside elements, Y minus 1 and Y4, in terms of the inside elements Y1 and Y2, then you'll get the algebraic equations, 2 equations in 2 unknowns. So you can solve them and obtain Y1 and Y2. Now, let us move on to partial differential equation. You know the classification of second order partial differential equations. If it is Laplace equation, Poisson equation, Helmholtz equation, they are of the elliptic type. If you have heat equation, it is of the parabolic type. If it is wave equation, it is of the hyperbolic type. We know this, okay, this classification. Now some examples are given. I'll pass these slides to the organizers. If you are interested, you can take it from them or you can email me also. Okay, so this is what you have. Some problems I have included here for the classification and just for completeness. So I'll now find out the finite difference approximation of partial derivatives. Again, I'll do the same thing. I'll take u of x plus h y. I'm keeping y as constant. I want a approximation for the x derivative. So I'll change only x to x plus h. So find out the Taylor series expansion, then find out an expression for the first derivative, partial derivative with respect to x. So you have u of x plus h comma y minus u of x comma y divided by h. Truncation error is of the order of h for forward difference. So uxx x comma y, that is this expression, which is very similar to what I did in the case of ordinary differential equation. Truncation error for central difference approximation is of the order of h squared. Truncation error for forward difference is order of h. Truncation error for backward difference is also order of h. So the central difference one is more accurate. So if I want the u of y x comma y, I have partial derivative of u with respect to y. What do I normally say? Treat x as constant. So just keep x as it is. Vary y now. Y plus k y. So divided by k. This is forward difference approximation for uy. Truncation error is of the order of h. Uyy is this. Okay, central difference approximation. So the truncation error is of the order of h squared. Now again, let us introduce some notation. U of xy, I take u I delta x, k delta t. This should be t, that is, okay, I'm sorry, they take this as t. So u of I delta x, what is h? That is plus delta x, k delta t. So you get u of I plus 1 delta x, k delta t. So when you have spatial variables, you subscripts. So you have I plus 1, which comes here. Then you have k with t, so that goes as superscript. So u of x plus h comma y, which is u xi plus delta x comma t, tk, that is written as u of I plus 1 k. So here again, I should have written this as t, this one also. Okay, all these are t's, that is. So you see, forward difference approximation for partial derivative with respect to x, they're all at the same time, but this is ui plus 1 minus ui. You divide. This is the forward difference approximation. Similarly, central difference approximation for this, central difference approximation for ut. This is, I'm sorry, ut xy. This is u, okay, u tt. Say if you have second order time derivative. So now let us take this approximation. What I'll do is I'll consider different values to delta x and delta y and see which one is appropriate. So now before moving on to the finite difference approximation, I should note here that there is one first order derivative in t. Okay, first order derivative with respect to time. Second order derivative with respect to x. So which means I require one initial condition. So I have t of x not equal to 1. That is the initial condition. I should have written initial condition here. Then this is second order in space. So I require two boundary conditions with respect to x. So t of x 0 t equal to 0, t of 1 t equal to 0. So I have two boundary conditions. Okay. Now let me between what is the range of x? The range of x is 0 to 1. So 0 to 1, I'll divide into 4 subintervals. I'll divide into 8 subintervals. Then I'll take different values of delta t And this ratio is important for me in finite difference approximation involving heat equation. So I'll take this delta T by delta X squared. I'll shortly tell you why we require this ratio. Delta T by delta X squared is half. Here it is also half, but the choice of delta T and delta X is different. Here the delta T and delta X are such that delta T by delta X squared equal to 1. Now, you see the problem. This is the heat equation which is given. What is the range of X? The range of X is 0 to 1. At the left boundary, that is X equal to 0. What is T? T is 0. At the right boundary where T equal to 1, where X equal to 1, you have T equal to 0. It is given over here. When X equal to 0, T equal to 0. When X equal to 1, T equal to 0. That is what I have taken here. Okay. Then what about this? Okay, that is the initial condition. At T equal to, this is time. At time T equal to 0, capital T equal to 1. So at time T equal to 0, that is this boundary, capital T equal to 1. So this is a hot boundary. These two are cold boundaries. Okay, now I divide the interval 0, 1 into subintervals like this. But here in this case, what is it? I'm dividing into fixed number of points. I'll come to that. I'll return back to that. So you have, now I'll consider one type of approximation, finite difference approximation of Schmidt. So dou T by dou T is you forward difference approximate, dou squared T by dou X squared, you do central difference approximation. So what is forward difference approximation for dou T by dou T? T of ik plus 1 minus Tik by delta T, that is equal to, now this is central difference approximation for dou squared T by dou X squared. Now I require to find out the solution at the next time level, that is k plus 1. So you see on the right hand side, all these quantities are at the kth level. Okay, so I find out the k plus 1th level in terms of the kth level. So you see here, okay, you see here, I am starting from T equal to 0 and I move to the next time level. What is the next time level? 1 by 32, because delta T is 1 by 32. Okay, so I start from here. Okay, here the boundary is hot, T equal to 1. So I find out the solution at the first time level, then next time level, then next time level, and so on. Okay, so you see here you get the ratio delta T by delta X squared. That was the reason why I took that ratio delta T by delta X squared. Now I told you we are going to take three choices of delta T and delta X, and we'll see what effect they have on the solution. So if I take delta X is 1 by 4, delta T is 1 by 32, I get delta T by delta X squared to be half. Okay, so now I have written very clearly here, this is the initial condition. Over here, what are these values? These values are all 1. Okay, and I find out the solution at the first time level. Then after finding out the solution at the first time level, I find out the solution at the second time level, then the third time level, and so on. Okay. So for the choice of that is for the choice that we have taken lambda equal to half, you'll see that Tik plus 1 is this. So when I say T of X not equal to 1, this is nothing but Ti0 equal to 1. Okay, I've written over here, when you have T not equal to 0, T11, everything equal to 1, because it is a hot lower boundary. What about the left boundary? Left boundary is X equal to 0. What is the right boundary? X equal to 1. So T of 1 T equal to 0, T of not T equal to 0. So you can write this as T of not K equal to 0. So T naught 1, T naught 2, T naught 3, etc. All those points on the left boundary, they are equal to 0. All the points on the right boundary, they are equal to 0. Now we'll find out the solution at the first time level. So I'll get Ti1 equal to half of Ti minus 1, 0 plus Ti plus 1, 0. Take I equal to 1, 2, 3 because the unknowns are 1, 2 and 3. So find out T1, 1, T2, 1 and T3, 1. You'll get them to be equal to 1. Now similarly we can next, having obtained the solution at the first time level, I now move on to the second time level. So this is the zeroth, this is the initial condition, that is 0th time level. This is the first time level. This is the second time level. This is the third time level, fourth time level. So you see at the first time level, at the boundaries they continue to be 0, but in between they continue to be 1. Slowly, when you move to the second time level, you see that 1 has been reduced to half, 1 remains as 1, 1 is reduced to half. Now, if I move to the next time level, third time level, this half is this 1 also becomes half. Is that clear? So you keep on solving at different time levels. Ultimately, when you take sufficiently large values of t, you'll find that all the values are equal to 0. Okay, so this is what it is. So when t tends to infinity, so what happens now? When t tends to infinity, time derivative will not be there because it reaches the steady state. So dou squared from the differential equation, what do you get? Dou squared t by dou x squared equal to 0, which means t is ax plus b. So I'll make use of the boundary condition t of 0 equal to 0, t of 1 equal to 0. You will get both a and b to be equal to 0. So analytically, the problem now has the solution t equal to 0. That is precisely what I got as t tends to infinity. So this is what I've got here. Everything is 0. So t equal to 0 when t tends to infinity. So those are the steady state values. So I take the second choice, which also gives me delta t by delta x squared equal to half. It's a smaller step size compared to choice 1. So you see that still the values reach the steady state, all t's become 0. Okay, so this is what you have. Now I'll take delta t by delta x squared equal to 1. The choice of delta x and delta t is such that delta t by delta x squared equal to 1. So if I take that and find out the solution at the first time level, till the first time level it is fine. Second time level also to a certain extent it is fine. Suddenly you see at the third time level that it becomes negative. Fourth time level negative. Fifth time level negative. So it continues to be not a regular set of values. So this is not an acceptable grid size. Delta t and delta x together are called the grid. And this is not an appropriate choice of grid size to solve the problem by the finite difference method. Okay, so you see that the step size in the first choice and the second choice, they were half. The ratio was half. What is the choice in the third? What is the third choice? The delta x and delta t are chosen such that delta t by delta x squared is 1. Okay, so you see that this does not yield proper result. So this can be understood if we assess how much error is there. The errors must remain bounded. Okay, so I'll say this. There are some terms which we have to use. So a differential equation, difference equation has to be consistent with the given partial differential equation if the truncation error at each xi tk tends to 0. Okay, so these are all theorem, which says that stability is a necessary and sufficient condition. Hello?
Yes, sir.
You're not hearing?
No, it's
It's
you can
fine.
hear. It's everything is fine.
Okay, fine. So we have an important theorem called the lax equivalence theorem, which says that stability is a necessary and sufficient condition for convergence. So it means if I do a stability analysis of the method, then that is enough because it takes care of convergence. There are two procedures of finding out the stability. One is called the matrix method. The other is called as the Fourier method or von Neumann method. This one. So I'll take one after another quickly. I require some theorems in order to study matrix stability. So I take the quotient matrix. It invariably in the problems that I do, not invariably, many problems that I do with numerical methods, I come across a tridiagonal matrix, meaning you'll have a main diagonal and a subdiagonal and a super diagonal. So three diagonals. So this is a tridiagonal matrix. You can similarly have a pentadiagonal matrix. You can have one more diagonal. You can have one more diagonal. All other values are zeros, mind you. Okay. Only these tridiagonals, they have some value non-zero, or it's a pentadiagonal. You will have 5 diagonals non-zero. Okay. All the rest of it is equal to 0. There are formulas to find out the eigenvalues of a tridiagonal matrix. So this is what you have. And if the diagonal is symmetric, then the eigenvalues lie between a minus 2 modulus of b comma a plus modulus of b. These are some standard theorems. So if lambda is an eigenvalue, then f of a will be f of a will have eigenvalue f of lambda. Okay. So now if you want the error to remain bounded, then the eigenvalue of that coefficient matrix, tridiagonal or pentadiagonal, the magnitude wise, it must be within a unit circle. Okay, so this is what you have. So let us see matrix stability now. I'll make use of the Schmidt method, forward difference approximation, central difference approximation here for spatial derivative. I'll rearrange like I did earlier. So I get a ratio delta t by delta x squared. So I make use of the boundary conditions, initial conditions, everything. So the grid values are obtained. So I'll get a matrix like this. So you see there is a main diagonal. Then there are two diagonals. One is the subdiagonal. The other is the super diagonal. All other these values are zeros. These values are zeros. So I find out the eigenvalue of this. So to find out the eigenvalue of this, I split the matrix into two. One that does not contain lambda, one that contains lambda. So if I find out the eigenvalues of that second matrix, then you'll see that the eigenvalue of the total matrix will be equal to this. For errors to be bounded, what did I say about the eigenvalues? They must be less than or equal to 1 from theorem 3. So lambda, the eigenvalue as the expression 1 take these values now. Take these values, inequalities. So you'll get lambda to be this. What is the maximum value of sine? The maximum value of sine is 1. So if I take this to be 1, so you'll get lambda less than or equal to half. So delta t by delta x squared must be less than or equal to half for stability. Okay. So you see there were three choices which we took. What was the choice for first one? Delta t by delta x squared was half. What was the stability condition? You did not get the correct solution. Okay, converged solution. So if I decrease delta x, what happens? Delta t decreases further. So the convergence to the required solution is very, very slow. The smaller the value of delta x, the slow the iterative scheme. Okay, slow the calculation. Now I'll take up a wave equation. Here speed has been taken to be 1. So I'll use central difference approximation for time derivative, central difference approximation for spatial derivative. So you'll write down like this. Now what do? You write down the quantities at the highest time level in terms of the previous time levels. What are the highest time level? What is the highest time level? K plus 1. What are the lower time levels? K and K minus 1. So I push all these lower time levels to the right hand side. Okay. So this is what I get. So I can make an error analysis. I'll just stop here and I'll just skip here. So I can find out xi less than equal to 1. Then that xi is nothing but this. Xi must be less than equal to 1. So that xi is given by this formula. So you'll again get something similar to what I did in the matrix method. So you'll get lambda to be delta t by delta x here. In the case of heat equation, what did you get? Delta t by delta x squared. In the case of wave equation, you get delta t by delta x. So that must be equal less than equal to half. Okay. So this is the condition of instability. Okay. So you see the heat equation and the wave equation have conditional stability. Okay. So this is what you have. I'll take up one problem on Dirichlet. So dou squared u by dou x squared plus dou squared u by dou y squared equal to 0. How many conditions on x? 2 boundary conditions on x, 2 boundary conditions on y. So you'll see here that x equal to 0 and x equal to 1. What is the value of u? That is 0. When x, what about this? When y equal to 1, okay. I'm sorry, this is 0. Okay, u of x0 equal to sine pi x. So that means y of 1, when y equal to 1, you have u equal to 0. When y equal to 0, then this is sine pi x. Okay. So I have this Laplace equation which is 0 on all the sides in this rectangular domain, but u is nothing but sine x. What is this line? This line is y equal to 0. So this should actually be y equal to 0. So I'll use all these approximations for the Laplace equation. I get something like this. I can write down the grid for solving the problem. Now, mind you, the problems that we did so far, what was the type of grid? The type of grid was either a square or a rectangle. But what are you finding here? You are seeing some crazy trapeziums here. So in this case also, here it is a triangle. So you are seeing different types of regions. Here you see a non-rectangular region because it has this part here. Okay. So how to go about doing this? So what you do is instead of saying x plus h, you say x plus ah. Instead of saying x plus h, x minus h, you take x minus bh. Y plus ck, y minus dk, likewise. So you retain that information. So expand by Taylor series. So you will get the expression for dou squared u by dou x squared, dou squared u by dou y squared. Substitute those approximations. You will get system of linear algebraic equations using which you can solve the problem. Now here again, this part, all the grids, they are not of this type. Okay, here one is triangle, one is trapezium, so on. So non-rectangular, that is geometry you have. So you solve this by approximating dou squared u by dou x squared and dou squared u by dou y squared at the grid points. So once you do that, you can obtain the solution u11, u12, u21 and u22. So that will give you 4 equations in 4 unknowns, and which you can solve by the Gauss-Seidel method. So these are some of the things which you can just go through, something on the standard diagonal 5-point formula. Now, when you have a 2-dimensional problem, you cannot solve it in such easy means. So you'll require the you'll require the stability condition in this form for this 2-dimensional equation. Okay, so the condition is slightly more involved. So then make use of finite difference approximation and use the numerical scheme. Okay, so all this you can get the solution using a Thomas algorithm for a tridiagonal matrix. You have a Thomas algorithm for a pentadiagonal matrix also. So here again, remember that this is a Laplace equation. There is no time derivative here. It is not a time evolutionary equation. You are simply solving a boundary value problem, no initial conditions. In the case of heat equation and wave equation, both of them are have initial conditions and boundary conditions. So they are called as initial boundary value problems. Whereas the case of the Laplace equation, okay, that does not have the time derivative, so you will have the boundary value problems. Okay, so when you have 2-dimensional heat equation, you'll have to adopt a slightly different procedure, which is called as the alternate direction implicit method. You solve in an explicit way in X, solve in an implicit way in Y, alternate that. Explicit, implicit, explicit, implicit. So it is called as alternate direction implicit method. See, these methods you'll have to sit down and work out, then only you would understand this. Okay. Within 1 hour, I'm simply unable to complete it. You can use finite difference approximation for problems in spherical symmetry with spherical polar coordinates also. So you have in r theta coordinates. So when you say r theta coordinates, so ri is I delta r equal to I h, theta j is j delta t, that's equal to j eta. So you make this substitution, adopt this convention. So expand the quantities by Taylor series. Okay. So you will get something like this. Okay. So r equal to r minus 1 thing will give you some approximation. These are some derivations for what is that? Different derivatives in. So you see here dou squared v by dou r squared, dou squared v by dou theta squared. Here are the approximations which you have. Okay. So first derivative also central difference approximation. First derivative with respect to theta, central difference approximation. Okay, all central differences. What is the truncation error? Order of h squared. In theta, I've called it as eta. Okay, so you can do that. There are a number of approximations. Number of books here which you can use very nicely explain how to go about solving this problem. Okay, so that is finite difference approximation for you. So what I'll do next is are you seeing this slide?
No, sir. No, sir.
No? Okay.
No, sir.
Just 1 minute, 1 minute. Now?
No, sir.
No? Now?
No. No, sir. No, sir.
No? Just a minute, then I'll have to close and open. What about now?
Sir, now visible, sir. Screen sharing, sir.
Yes.
Understood.
Okay. So what I'm going to do now is I'm going to introduce to you two very nice procedures of solving really complicated problems, and they can be done in a very, much simpler manner than what people normally do in the case of computational fluid mechanics. So you see here that I have given the title, you too can do CFD now. Okay, earlier CFD was thought of to be used to solve complicated problems. The methods are quite simple to use. Okay, now what is the idea behind the methods? We are going to make use of parabolic solvers, meaning what are methods, approximate methods for parabolic
Sir, you are not audible, sir.
of parabolic partial differential equations. Okay, so this is what you have. So I'll cover this now. Now, if for those of you who want my email address, you can use one of these two. Okay, please note down. You can just email. I'll pass them on to you. The slides, in case you want, I'll pass them on to you. You can just email me, and I shall send you the slides. Okay, or if you have any doubts, you want some clarification while doing it, then I would respond on these two emails. Okay, so I'll skip this. Yes, this one. So if you take a function f of x, now this is nothing but the Taylor series expansion. Okay, a Maclaurin series expansion about x equal to 0 it is. So now what I'll do is I'll leave alone x, so x to the power of k. I'll only consider 1 by k factorial into dkf by dxk evaluated at x equal to 0. So that because I am evaluating at x equal to 0, this is independent of x. So this will now be a function of k only. So I'll call this entire thing as capital F of k. So if I use the notation f of k here, what will happen now? Summation k equal to 0 to infinity x to the power of k into fk. So I get this f of x equal to summation k equal to 0 to infinity over here x to the power of k. What have I called the remaining one as? I've called it as f of k. So I have written it here. So my function f of x, I've written it down as in terms of a transform now. So that is called as a differential transform. So what did I do there? The small x, okay, the small f gets converted to capital F, and that transform which I get, I use to construct my f of x again. So y of x becomes yk, g of x becomes gk, meaning this is a linear transformation. Okay, these two tell you that. I can find out the transformation of derivatives. I have done it here. I can find out the transformation of product of two functions. I have written it here. This is like your convolution theorem. Okay. I can find out the differential transform of x to the power of n in terms of a Dirac delta function here. Okay. So differential transform method is the one which can be used. So I'll show you how to use them. Now, for example, suppose I have a differential equation like this. what is omega? Omega is nothing but vorticity. Okay, in fluid mechanics, or don't worry about fluid mechanics terms. Simply think of this to be a Laplacian. So if omega is this Laplacian, so I have an equation in this form. It is parabolic. What I do is I now see here.
यहाँ कोई किसी को कम नहीं है.
हाँ, तुम बता दिए कि भाभी वो पूजा कराई थी, आपको इसलिए नहीं बोला है क्योंकि रीता और बाबू आप पे डिपेंड है. रीता किचन में
Arvind Mishra ji, Mr. Arvind Mishra ji, kindly control your voice.
भैया खाते पीते नहीं.
Arvind Mishra ji, please mute your voice.
करके नहीं पड़ता.
I just personally inform them, sir. Please, sir.
Okay. So you'll see here that when you find out the product of two functions, I mean the transform of the product of two functions, you will get some summation here like convolution theorem. Okay. So I have product of two functions here. I am finding out the differential transform with respect to time of this equation. Here I use the product. Here I use this one. What is that? Derivative. So I'll get k plus 1 gk plus 1. So you see your time derivative. What have I got? K plus 1 into w of xy k plus 1. So here I get the convolution product. Here I'll gain the convolution product of the product of two functions. Then here these are x and y derivatives. So I'm taking differential transform with respect to time. So these are unaffected. These are x in case of t. Hello? Can you please mute yourself?
Yes, sir. I just inform them, sir.
So this convolution product has been written over here in the way that I wrote earlier. So now if I use the finite difference approximation for the spatial derivatives, I can simply solve system of equations and get a solution for this problem. Okay. And the restriction on delta t is not all that stringent as you see in the case of finite difference approximation. Okay. So the type of problem that we considered, I'll just show you. We consider a driven lid problem, a very complicated problem. We went up to Reynolds number 1000. We were able to capture the secondary flow here. Okay, you see these are secondary flows which are generated at the corners. You don't see in these cases because the Reynolds number is quite small. Okay. Similarly here, now here what is happening is the upper plate is also moving, the lower plate is also moving. So you get two cells instead of one cell. Reynolds number is 1500. So you see these secondary flows being generated here. It is also beginning over here. So you see secondary flows over here. So you see that the complicated problem of a driven lid problem, you are getting the solution for that, okay, with the differential transform method. Okay, so that is what you have. Everything, whatever is seen in this problem can be captured by the differential transform method coupled with the finite difference method. Everything possible can be captured. So you see here large Reynolds number, small Reynolds number, everything is being seen here. Now here what is happening is you see a tilt of the cell. Why is that? the upper plate is moving in this direction, lower plate is moving in the opposite direction. Okay, so there is a shearing of the cell, so you see a slanting cell over here. Then when you increase the Reynolds number, you'll get secondary flows in this problem also. So same thing, you'll see that the secondary flows become stronger when Reynolds number is increased from 1500 to 2500. Now this is a very, very interesting problem, the lid driven cavity problem. So what did we do? Okay, I'll go back and mention this. What did we do here? I took the differential transform with respect to time. So I got rid of time derivative. So this equation reduced to an elliptic equation. So what was a parabolic equation? I reduced it by differential transform to an elliptic equation. So the elliptic solver that I have using the finite difference approximation, I am able to use in this case. Whether it is regular boundary, irregular boundary, or whatever it is, because it is a Laplace equation, it is easier to solve. So my parabolic problem I have converted into an elliptic problem. So you see this title here. What have I said? Elliptic solvers for parabolic partial differential equation. So I had a parabolic partial differential equation. Using differential transform, I converted it into a elliptic differential equation. So you have an elliptic solver for a parabolic partial differential. Next problem that I am going to do, I am going to do a parabolic solver for elliptic partial differential equation. I'll show you how. So what I'm doing here is the steady omega. Okay, I have an additional magnetic field term. Okay, so I don't have time derivatives here. Now we should remember this. When you have the heat equation, when you have the wave equation, higher dimensions, 2 dimensions, 3 dimensions, unsteady problem, when you consider the problem for infinite time, meaning for very long time, the time derivatives become unimportant, and that is what is called as the steady state. Okay, so this problem is one of the steady state. So the idea in this formulation is to think in the following way, to think of this problem as being the steady state of some unsteady problem. Okay, so we'll see this. You see this here? So I'll introduce the time derivatives artificially. It was not there in my problem. So what I'll do is I'll simply introduce that. What have I done here? I'll take this to the left hand side. So take this to be dou psi by dou t. Now take this to the other side and take that to be dou omega by dou t. So when I see this problem at very long time, what happens? I reach the steady state, so this will become 0. So because psi keeps on decreasing with time, omega also keeps on decreasing with time. So you'll see that this becomes 0 ultimately when you take very large values of t. So then when this is negligible at that large times, then this problem will be the same as what I have over here. So I am introducing pseudo time derivatives here. So the problem, which was basically an elliptic partial differential equation, will now have a parabolic formulation for it. So I am considering a parabolic solver for an elliptic differential equation. So what do I do here? That is important. Now take this, okay, take this particular problem. So I have, I'm going to make use of finite difference approximation. So I'll approximate dou psi by dou t. Okay, I'll approximate dou omega by dou t. So let me do that. So what do I get? What do I get there? I'll get psi of n plus 1. Okay, so you see here psi of n plus 1 minus psi n. Okay, I think, okay, I can do it for you. Just a minute. Okay, remember this. Dou psi by dou t is Laplacian plus omega. I'll just take one equation and then I'll do it for you. Yes. Okay. So what was the equation? I'll just write it down for you. What was the equation? Dou psi by dou t, that's equal to dou squared psi by dou x squared plus dou squared psi by dou y squared plus omega. So before I do anything, what am I doing now? I'm discretizing. I'm not considering all time, but I'm considering, say, T0, T1, T2, etc. discretized points. So what am I doing with x? I am again considering not all points x, but some points xi, not all points y.
Sir, not able to see. What are you writing, sir?
You're not seeing?
No, sir.
Okay, एक minute. Now?
Yes, sir.
Right.
Yes, sir.
Yes. So you see here that this was the differential equation I was trying to solve. Okay, I'm taking one of the equations there. So I'm not considering all time, but I'm considering some time T0, T1, T2, etc. discrete times. Not all points x, but x0, x1, x2, etc. Similarly, y. So now what I'll do is, instead of writing dou psi by dou t, I'll just write it as dou psi I k. Okay, this is dou psi I, dou squared psi I k, because I'm considering the values of psi at what points? Tk, xi, okay, yj. So I also require j over here. So this is omega ijk. This is all. This also requires j. This also requires j. Okay. I refers to x, j refers to y, and k refers to time. Okay. So this is what I have. Now I'll make use of forward difference approximation. So what do I get there? I'm sorry, I'll just rub this. So psi of I comma k j k plus 1 minus psi of ij k by delta t, that is equal to this quantity, whatever it is there. So what have I done here now? You just observe here. So now I want psi ij k plus 1. So I have multiplied this right hand side. What have I done? I have taken this delta t multiplied with this. Okay, so I'll do that. Okay, so I'll multiply it by delta t here. Okay, now what I'm going to do is push this psi of, now remember on the right hand side you have everything at ijk, but what about the left hand side? Only this is at ijk. Okay, but whereas this one is at ij k plus 1, higher time level. Okay, so now I'll change everything. Okay. So what happens? I'm pushing it to the right hand side. So this becomes psi ij plus. So now you see that all these are at the kth level at different positions xi, yj. Okay, so I can find out this using the methods. Okay, so I'll now shift to the other one. Okay. Yes. You are seeing now?
Yes, sir.
Okay. Okay, I was taking this. Then you see that I started with this. Okay, so if I rearrange there, this is exactly what I get. Okay, now what has been done here is yet another manipulation has been done. You see here that the x and the y's are together. Okay, similarly here the x and the y's are together. So now what happens is, what I do is I factorize the two. I'll show you how I factorize the two. Oh, I'm sorry. So you take this. Now if I multiply this, what do I get? I get 1. I get minus delta t into dou squared by dou y squared minus delta t into dou squared by dou x squared, but I get plus delta t squared into mixed derivative, right? Just see that now. Okay. What do I have here? I have only 1 minus delta t dou squared by dou x squared minus delta t dou squared by dou y squared. If I write down as a product, I am getting one additional term. Okay. So I have factorized this. Why have I factorized this in this way? I fully well know that delta t squared is quite small. Is that clear? Similarly, I factorize this. In the idea is the same. I factorize this. I isolate the x derivative and the y derivative. But now you should note the following. This dou psi by dou y, you might be thinking this psi is coming here. This dou psi by dou y is at the nth time level. I'm trying to solve where? I'm trying to solve at the n plus 1th time level. So this will be known. Okay, so this factorization, again on the same reason as this, will have delta t squared, which will be quite small. Okay, so once I do that, what happens? When I reach the steady state, that means for very long time, what happens? And when I reach the steady state, psi n plus 1 will be the same as psi n. Two time levels will have the same values. So the value psi n plus 1 along with these two derivatives, what I do, because I did not, I considered additional terms, what I do now is I add them up, but at the nth time level. Similarly, I'll do it here, add this at the nth time level. Okay, so because psi n plus 1 at the steady state, psi n plus 1 is the same as psi n. So this delta t into delta t, dou squared by dou x squared, dou squared by dou y squared will be the same as this. Okay, so at the steady state, they will not pose any problems. So that is the thing that is done. So what do I do now? What do I do now? I have a very nice problem. I simply solve the y part, then move to the x part. Okay, what do I do here? I take the y part, and then from that I determine the x part. Okay, so I simply solve like one dimension. So solve this, then once I know this, okay, once I know that, once I know f over here, I can use it here and solve for psi n plus 1. So this is what you have. Okay, so this is how it is done. Similarly for the other equation, so you solve an elliptic equation as using a parabolic thing can be captured. So the results coincide. Our results which we got coincide with all the standard results which are there in the literature. So it's a wonderful whom I have not added. I had some wonderful students. I should acknowledge that here. My students thought they were being taught by me. The fact is I learned from them. I profusely thank each one of them for educating me through and through. Now this is the Great Wall of China. So you can see me over here. Limitless. It's just conveys everything. So thank you very much. I love my math. I'm sure you love your maths too. Thank you very much.
Thank you very much, sir, for interesting lecture from your side, sir. And now I want to invite any participant who have any discussion may ask to question to respected Siddheshwar sir. Please participant. Any of you have any question? May ask.
Hello.
Hello.
Sir, I'm Tejas Shah from VNSU Salzburg University.
Yeah.
Sir, I'm working on the same method that you mentioned, differential transformation method.
Yeah.
But I'm starting working on the method and I'm stuck at the point I'm solving the fluid flow to porous media problems. That is vertical groundwater recharge problem. But
Okay.
that's okay. That contains initial as well as boundary values.
Okay.
But I stuck at the point when I transform the boundary condition using the differential transform. At the some points, I get in the transformation to boundary condition. I got stuck where I got the values out of the transformation of the conditions that contradict the values of initial and boundary conditions.
No. When you see, let me just explain to you. You have an initial boundary value problem. Is that right?
Yes. Yes.
So you.
Sir, I cannot hear you. Hello. Hello.
Yes, sir. Network
Hello?
issue, I think.
Okay.
Yeah. You apply differential transform with respect to time.
Yes, sir. With time and depth. Hello.
With respect to time, you are applying differential.
Actually, sir, there is a network issue. I cannot hear you.
नेटवर्क इशू आ रहा है आपको भी.
Siddheshwar sir, I think there is a network issue from your side, sir. So you are not so much clearly audible, sir. Breaking is there. Hello, Siddheshwar sir.
Hello.
Sir, just wait. I'm just trying to connect with PG. Maybe some network issue is there. Just a minute, sir.
Okay, sir.
Yes. Mahesh. Yes. So you are taking the differential transform with respect to time.
Yes, sir.
And what do you do with the spatial variables?
Sir, I have to find the vertical moisture content at the different time level and
I don't
different
want
depth.
the fluid mechanics.
Yes, sir.
Differential equation wise, what are you doing with your spatial derivatives?
Sir, I have to find. I can't understand you. What you mean to say?
See, you have time derivatives.
Yes,
You have
sir.
x derivative, y derivative. Is that right?
Yes, sir.
So you are applying differential transform with respect to time.
with respect to time and with respect to depth also, sir. My domain is depth and time.
No. Yeah, see, I'll tell you, you don't apply differential transform with respect to depth.
Okay.
You apply differential transform with respect to time, and
Okay.
for spatial variables, you use any other method that is better.
Okay.
Yes.
Okay. One more thing I want to ask that is there is any need to check the convergence for this differential transform method?
Yeah, there is. You can find out the limitation on delta t. You can find out.
Yes, sir. Okay. Sir, thank you so much.
Yeah.
Any other participant? Some questions are there in chat box. May ask directly. Pradeep sir, am I audible, sir?
Yes.
Okay, sir. I just want to read some question from chat box, sir. Mr. Pawan Shrestha have a question. Can the Euler equation be solved by the same method by professor you mentioned?
One
May I
minute.
repeat, sir? Can the Euler equation be solved by the same method by professor you mentioned?
Pawan, there is there is nothing like a preference for Navier-Stokes equation by the differential transform method. It simply you just treat any differential equation by this method. Okay, there is nothing like Euler not being preferable or Navier-Stokes being preferable. You can apply. Yes.
Sir, one more candidate is there, Kabita Lutiel. She
Yes,
is asking, sir.
Yes, I read that.
Yes, sir.
I read
Yes,
that.
sir. Yes.
Okay,
sir.
Robin type boundary conditions you can definitely solve. As I told you, my choice for the differential transform method is differential transform method only for time derivative. Spatial derivative you do by any method, finite difference, or you make use of Fourier transform, or you make use of that is finite element, whichever method. You, so far as time any other?
Hello.
Yes.
You told that for the time derivative differential transformation for other methods. So there is a method, hybrid differential transformation method, that contains finite combination of differential transformation and finite differential transformation, finite difference method. So can we use that for the other variable? Hello.
Sir, you are not audible, sir. Pradeep, sir.
Hello.
Audible. Yes, sir, you are audible.
Yes. I would suggest that you make use of differential transform with respect to time only. Don't use two-dimensional differential transform.
Okay.
Yeah.
Sir, you are not visible, sir.
Not visible. Now?
Now fine, sir.
Okay. So that is what I wanted to say.
Okay. Once again, any other query? Otherwise, we are going to off this session. Participants, any question? Okay. Okay, sir. I think no question left now.
Okay.
Lot of thanks, sir. Very interesting and informative session from your side, sir. And we are very happy to have you in our lecture session. So all will be benefited definitely, sir.
Yes.
So we are thankful and grateful to you. Lot of thanks, sir.
Okay. Okay.
Thanks,
Thank you
yes,
very
sir.
much. Thank you.
Thank you, sir.
Thank you.
Okay, sir. Dear participants, after lunch session at 2:30 we will meet again on the same link. Dr. Bir Singh Baduria Sahab from Central University Lucknow will be there to deliver an expert lecture as an application of previous topic. Okay, thanks a lot. We will meet again at 2:30 sharp.